Hello fam, welcome back to my online tutorial. In today's class, we have an exciting problem on the limit of a function. Now, in solving this problem, I am going to use two methods. The first one is the regular algebraic simplification. The second one, I shall use the famous L'Hopital's rule of differentiation. Now, without any further ado, let us look at the solution together. We have to evaluate the limit of this function as x tends to 2, the square root of x squared plus 5 minus 3 divided by x squared minus 2x. Now, it is customary and traditional that if you have a function and you are evaluating the limit, we plug in the limiting value into the function to see how it behaves. So if I plug in x equal to 2 on the numerator, I will have square root of 2 squared, which is 4 plus 5. That will be the square root of 9, which is 3. 3 minus 3 is 0. Then on the denominator, if I plug in x equal to 2 here, I'll be having 2 squared, which is 4. 2 times 2, which is 4. So 4 minus 4, 0. So we have a case of 0 dividing 0. And this is an indeterminate function. So now that this function is indeterminate, what we have to do is to try to simplify. Now, in simplifying this expression, we need to use the algebraic method that we possibly can. Now, the reason why we try to use algebraic method first is that if we are using calculus by differentiating the numerator and denominator, for somebody who hasn't taken class in calculus, you cannot do that. So we shall try to simplify. But before we start, I shall take our minds back to what we know, about radicals. If I have a fraction, 1 upon the square root of 2 plus 3. Now, because the denominator of this fraction is a radical, what we do in mathematics is to rationalize the radical. Now, in rationalizing the radical, what you do is to take the conjugate of this surd and use it to multiply both the numerator and the denominator. So if I were to rationalize this fraction, I will multiply it by root 2 minus 3 on the numerator, root 2 minus 3 on the denominator. This is just to give you an insight to what we are going to be doing with this expression. Now, look at the denominator carefully here. We have a difference of 2 squares. Now we can check that out. Root 2 multiply root 2 is going to give us root 2 squared. Root 2 multiply negative 3, that will give negative 3 root 2. Here, 3 multiply root 2, that will give us positive 3 root 2. Then again, 3 multiply negative 3, that's going to give us 3 squared. So as you can see, negative 3 root 2 plus positive 3 root 2 is going to subtract out. We are left with the square here, subtracted from what? Okay, minus the square here. So as you can see, to give us a difference of 2 squared. Now, with this, we are going to treat this expression likewise. Now, we are not used to rationalizing numerator, of a surd, but it is doable. That is just to help us simplify. So, it's going to give us limit as x tends to 2, square root of x squared plus 5 minus 3, multiplied by the conjugate, the square root of x squared plus 5, then plus 3, upon x squared minus 2x, in parentheses, repeat the conjugate, x squared plus 5, then plus 3. As you can see, the numerator here is a difference of 2 squares. So I will write limit as x tends to 2, the square root of s squared plus 5 all squared minus 3 all squared upon. Now, I shouldn't attempt to expand these two parentheses. It's going to make the word more complex. Rather, I shall simplify or factorize this s squared minus 2x. As you can see, s squared and 2x has a common factor, which is 2x. I will take out x. Now, I will use x to divide s squared. That gives me x. I will use x to divide negative 2x. That gives me negative 2. Then I will just rewrite the radical. Now, the square root here will cancel out the square root. So you are left with s squared plus 5. I will write limit as s tends to 2, s squared plus 5 minus 9 upon s into s minus 2 into square root of s squared plus 5 plus 3. So we have. Now 5 minus 9 is negative 4. I'll have limit as s tends to 2, s squared minus 4 upon s into s minus 2, then the square root of s squared plus 5, then plus 3. Put this in parentheses as well. Now, if you check the numerator, 4 is a square number. So I can write s squared minus 4 as s all squared minus 2 all squared. And this is going to give me s plus 2 in one parenthesis, s minus 2 in another parenthesis. So in place of s squared minus 4, I will write s plus 2 into s minus 2. Now, we are gliding towards the solution. So this is going to be limit as s tends to 2, s minus 2, s plus 2, all divided by s into s minus 2 into the square root of s squared plus 5 and plus 3. So s minus 2 will cancel out. So you can now see that we have simplified this expression and we have watered it down to a level where we can now plug in the limiting value. Now what is left here is going to be limit as s tends to 2. On the numerator we have s plus 2 all over denominator we have x into the square root of s squared plus 5 then plus 3. So if we plug s equal to 2 here, that's very primary arithmetic. We are going to have 2 plus 2 divided by s is 2 on the denominator into the square root of 2 squared plus 5 then plus 3. Put a parenthesis there as well. Now 2 plus 2 is 4 on the numerator. Inside this radical we have 2 squared, which is 4 plus 5. That will be the square root of 9. I will write 2 into the square root of 9 then plus 3. Then I can write this to become 4 upon square root of 9 is 3. 3 plus 3 is 6. This one will be 2 bracket 6. So I'm going to have 4 divided by 12. So if you write this fraction in its lowest term or form, you are going to have 1 on 3. So this is the answer to this problem. Now in the second method, we shall use the L'Hopital's rule. Now, L'Hopital's method is very simple. For those who are grounded in calculus. So what he says actually is this. We have a limiting function that is indeterminate, just like the one we have here. L'hopital said we should differentiate the numerator and differentiate the denominator separately and plug in the limiting value. That was what L'hopital did. Now, that means that we are going to say that limit as s tends to 2, the differential operator d by dx of the square root s squared plus 5 minus 3 all over the differential operator d by dx of s squared minus 2x. This is the work of L'hopital. So you must be grounded in calculus to be able to do this. Now for the numerator, what we have there is the differential operator of the square root of s squared plus 5 minus 3. So this actually implies that we need to differentiate s squared plus 5 under a square root. Then we need to differentiate 3, which is a constant. Now, to differentiate the constant, we get 0, so that's off. So our main focus shall be the radical, the square root of s squared plus 5. And I cannot differentiate this. I have to write this one in exponential form. That means that I am going to find the differential of s squared plus 5 all raised to the power of half. So this is an interesting question. I wouldn't say it's difficult. I wouldn't say it's complicated, because this is the beauty in mathematics. And the mandate of this project is to make mathematics and physics simpler again. Now, d by dx here is a differential operator, like I said. So if it acts on this function, it differentiates it. And again, this is not a regular algebraic function. This is a chain function, s squared plus 5 all raised to the power of half. Normally, what we do here is to use a method we call chain rule, where we need to substitute, and differentiate. But now I'm going to do this directly. That's not a rocket science. It's not a rocket science at all. It's actually a simple process. I will differentiate this entire entity. And before I do that, we all know we have y equal to s to the power of n, dy upon dx is equal to n multiply x, then we subtract 1 from the exponent of the power. So this is the general formula for differentiating linear algebraic functions. Now if I apply this here, like I said, I will differentiate the entity. That's going to give me by dx. I'm just rewriting this step again. S squared plus 5 raised to the power of half, which is actually equal to half into s squared plus 5. Then I will subtract 1 from this exponent, that becomes a negative half. Then I will multiply it by the differentiation of s squared plus 5, and that's 2x. So as you can see here, 2, we cancel out the 2 here, we are left with x. So this is going to give me, x into s squared plus 5 raised to the power of a negative half. Now, s squared plus 5 raised to the power of negative half. The negative exponent there is not friendly. The greatest enemy of algebra, like I've often told students, is negative signs. So if we have a negative sign and we have, the opportunity to work around it, then we can do that. So I will use the inverse law of indices here, where I will take the reciprocal of this function. That becomes s multiply 1 all over s squared plus 5 all raised to the power of half. So the inverse law of indices states that if you have a negative exponent, you take the reciprocal of the positive exponent. So this is going to give us s divided by s squared plus 5 raised to the power of half. And if you have a number, a variable, and expression raised to the power of half, it means the square root of that very expression. So I can write this to be s upon the square root of s squared plus 5. So this is the differential value of the numerator. Then for the denominator, we do likewise. So I will use the differential operator to act on s squared minus 2x. Now, it's very easy. It's actually differentiation by summation and difference. All I will just do is to differentiate s squared, which will give me 2x. 2 multiply x, that's 2x. Then 2 minus 1, that's 1. So the power here is actually 1, but we don't need to write it. Now, if I differentiate negative 2x, the s is actually my concern. The power is 1. I will use 1 to multiply 2. Then if I remove 1 from 1, I will now be having s to the power of 0, which is 1. So this is the differential value of the denominator. Now that I have taken or rather done the differentiation of the numerator and denominator separately, I can now write limit as s tends to 2. I will take the differential value on the numerator, which is s upon square root s squared plus 5, all divided by the differential value of the denominator, which is 2s minus 2. Now, at this level, we have watered it down, we have distilled it, refined this problem, and we can now plug in our limiting value. Now, if we substitute s equal to 2 here, we are going to be having 2 divided by the square root of 2 squared plus 5, all divided by 2 multiplied 2 minus 2. And this is going to give us 2 divided by 2 squared is 4 plus 5, that's 9. That's the square root of 9, all divided by, here we have 2 multiplied 2, 4. We remove 2, that's 2. So at the end of the day, the answer or the solution to this problem is already staring at us. Square root of 9 is 3. This will now be 2 upon 3 divided by 2 upon 1. Now, if you have a division in a fraction, a pair of fractions, you invert or reciprocate the second fraction and turn division into multiplication. So at the end of the day, 2 will cancel out. We are going to be having 1 on 3 as our answer. Now we have come to the end of today's class. As you can see, as always, it is an exciting problem. It's actually a great solution. Please give this video a thumbs up. Continue to like, watch, and share our videos. See you next time. Bye.